Welcome to a quick overview of the research we do at Monash School of Chemistry on the fascinating chemistry of what we call solar fuels. I'm Professor Doug MacFarlane, and along with colleague Alexandr Simonov, we lead a group of about 30 students and postdoctoral researchers who are dedicated to understanding how to turn renewable energy into liquid fuels. The attraction of liquids, as compared to, for example, batteries, as a store of renewable energy, is that these are easily moved around, just as today we move around crude oil and LNG. And indeed, one of the key goals of our research is to develop ways to utilize the enormous potential that Australia has to generate renewable energy, quite unlike anywhere else in the world, and to turn that into a form that is easily exported to markets overseas. So what are our targets in this respect? Our work started more than a decade ago on hydrogen made quite literally by splitting water. Making this process more efficient and less expensive remains an important goal, and we have some very bright young minds here focused on developing new compounds that can act as catalysts for this purpose. More recently, it has been proposed by us and other groups worldwide that ammonia may be an even better liquid fuel. Ammonia is much more easily liquefied, and the international shipping of ammonia on bulk tankers for fertilizer production is already a very routine matter. What is less well known, but quite exciting, is the range of things that ammonia fuel can be used for, including marine engines, buses, trucks, and mining vehicles. Basically, anywhere diesel is used, it can be substituted by ammonia. A recent study has even concluded that ammonia, in many respects, is a superior fuel for jet engines compared to traditional kerosene. So please join us as we take you on a tour of the labs and the teams to show you what we're up to.
A typical solar fuel plant can be simplistically separated into the two major arrays of units. A solar harvesting photovoltaic panel that transforms sunlight into electricity, and so-called electrolyzer devices that further transform electricity into fuels. Fuels that can be used to power a lawnmower, a car, a ship, a house, essentially anything where we would normally imagine the requirement of an immediate, on-demand supply of power. The distinction of solar fuels from the conventional ones is that their generation and utilization produces minimal, theoretically zero, emissions, and equally importantly, they are essentially infinite on the timescale of humanity. At Monash, a large and diverse team of scientists and engineers aims to advance essentially all technologies in this sustainable cycle, from the fundamental understanding of the way the photons are converted to electricity, to the creation and fabrication of the industry-ready electrolyzer prototype devices. The work on the next generation photovoltaics is majorly led by our colleagues at the engineering department, Professor Udo Bach and Professor Jacek Jasinov. The new solar cells we develop together will be quite different to what you can or might have already installed on the rooftop. They will be different in terms of the cost of the fabrication and eventually in terms of energy efficiency. This will not only make the solar photovoltaics much more affordable to the general public, but equally importantly, it will bring the global prices for electricity down. And transformation of this electricity into high energy density fuels is what we are doing at the School of Chemistry at Monash. So how does the electrolyzer work? In essence, you can consider this process being similar to charging a battery, like a battery in your car or in a phone. However, instead of storing energy inside the battery, the electrolyzer will generate a chemical compound, a fuel, that can be continuously collected. And the electrolyzer can be run further and further indefinitely while generating more and more product. In other words, we generate fuel continuously from the electricity. Amazingly, these devices are quite simple, nothing overly sophisticated as one might expect to see in the frontier energy technology. The core of the electrolyzer are two electrodes, one negatively charged and another positively charged. For example, when we provide a broadly abundant feedstock like water to the positively charged electrode, we'll produce oxygen, a gas that we breathe. If we provide water to the other electrode, to the cathode, we'll produce hydrogen. Hydrogen, which is the cleanest fuel you can imagine. Why is it the cleanest fuel? Because when it is burnt, in other words, combined with oxygen, the only product is water again. In other words, we have completed a fully sustainable cycle using the only one resource, sunshine. So why are we not there yet? Why this amazing technology is coming to industry only now but not years back? Previously, the key reason was expensive electricity, but this will not be a problem anymore quite soon. The remaining more topical problem is the durability of the key devices, of the electrolyzers, and more specifically of the electrodes within. Another key element of electrolyzers is the electrolyte, either liquid or solid compound that completes the circuit inside. Our goal is to ensure that all of these so-called electromaterials and devices based on these electromaterials operate as efficiently and as long as possible. How do we achieve this? Actually, the answer is not that simple because there are too many exciting things we do in our labs. Obviously, the work starts beyond the laboratories when we devise the ideas, often through the collaboration with our outstanding theoretician colleagues. And then the real magic happens when we transition our new ideas into reality. Material synthesis and fabrication are one of our core activities that require a lot of skill and are often akin to art. We search the conditions through the variations of temperature, pressure, the nature, and the amount of the starting compounds, the way we mix them and bring together everything with one goal, to obtain materials with the properties required for the final application. We create our materials under highly reactive environment or under completely inert atmosphere, at temperatures where nitrogen becomes a liquid or at temperatures where metals start to evaporate, under ultra-high vacuum or at pressures as those several hundred meters deep underwater. We use ultrasound, lasers, microwave radiation, and even our electrolyzers to create new materials and electrodes. Once the material is synthesized, it needs to be characterized. And we do this with a broad range of high-end techniques that, for example, use an electron flux, X-rays, or other forms of irradiation. And we're exceptionally lucky to have access to one of the world's best facilities here at Monash Clayton campus, as well as at the Australian synchrotron, which is just across the road. When even more advanced modes of the characterizations are required, we go overseas and work with our colleagues, for example in Germany, in Berlin, at the BESSY-2 synchrotron facility. The most exciting part of our work comes when we test our materials, when we understand where the initial idea works and the material indeed operates in the way we expect it, or, occasionally, when we find out that it actually behaves quite differently and we need to take a step back and reconsider our strategy. We design and construct a variety of different devices, many of which are electrochemical cells where electrical energy is used to create new chemical compounds, for example, fuels like hydrogen and ammonia. Each process requires a specific design of the device and overall experimental setup, which fosters imagination and inventiveness of our bright research team. Some processes are simple enough to be run in an electrolyzer that would look like a test tube. But much more commonly, more elaborate devices are required to maximize the efficiency of the way electricity, reactants, and products flow through. Eventually, when the electrolysis is over, the products need to be analyzed, which now requires some analytical skills from the team. We use a wide range of very different methods that vary from the simplest measurements of mass and volume to much more advanced techniques that study the interaction of the produced compounds with different forms of irradiation like visible infrared, ultraviolet light and X-rays, with magnetic field, or with other materials and compounds. In the end of the day, through this analysis, we can understand not only how much, for example, ammonia was produced, but also the changes that occurred in the system during the electrosynthesis. This video provides only a brief overview of our activities at the Monash School of Chemistry towards the advancement of the solar fuel technology. But we hope that it does provide an impression of how diverse, multidisciplinary, and captivating our work is. Through this, we aim to create an environment where the next generation of researchers can not only produce cutting-edge science, but also acquire a very broad range of skills. Skills that will support their careers, skills that will support technological breakthroughs, and skills that will support our future.